Let's get started. To explain the motion of large objects, Newton's laws of motion are typically used. These laws help us understand properties such as position, velocity, and momentum. However, when it comes to extremely small particles like atoms, Newtonian mechanics no longer applies. In such cases, quantum mechanics is used instead. To describe the behavior and position of electrons within atoms, scientists rely on Schrödinger's equation, from which the concept of quantum numbers is derived. Next, we should understand that each electron in an atom is assigned a unique set of quantum numbers, not for a whole atom. In general, a set of quantum numbers describes the quantum state of a single electron in an atom. Let's look at an example. Carbon has 6 electrons, so we can write 6 different sets of quantum numbers, one for each electron. For instance, one for an electron in the 2s orbital, and another for one in a 2p orbital. Here are the 4 quantum numbers, along with their designated symbols, N, L, Ml, and Ms. First, we need to understand the term N, which is the principal quantum number. It defines the energy level or shell number where a specific electron is located. It can take values like 1, 2, 3, and so on. You can also use K, L, M, N, O, so on instead of number. The energy increases as the value of N increases, as shown in the graph. An electron in hydrogen occupies energy level 1. In helium, both electrons are also in energy level 1. In lithium, 2 electrons fill energy level 1, and the third electron enters the 2s orbital in energy level 2. The next quantum number, orbital angular momentum, quantum number, which follows the principal quantum number. It determines the shape of the orbital. For s orbitals, the value is 0. For p orbitals, it is 1. For d orbitals, it is 2. And for f orbitals, it is 3. Each energy level can contain different types of orbitals depending on the value of n. For example, for hydrogen's only electron, n equal 1, L equals 0, since it occupies an s orbital. For each electron in helium, n equals 1, L equals 0, again due to the s orbital. For the last electron filled in the carbon 2p orbital, n equals 2 and minus equals 1, because p orbitals correspond to L equal 1. If we consider an electron in the 2s orbital, n equals 2 and blank equals 0 because it's an s orbital in the second energy level. The third quantum number is the magnetic quantum number, which determines the orientation of the orbital in space. The s orbital is spherical in shape, and its magnetic quantum number is always 0 regardless of the energy level. The p orbitals are dumbbell-shaped and oriented along the x, y, and z axes. Their magnetic quantum numbers are -1, 0, and +1. D orbitals have a more complex cloverleaf shape, with 5 different orientations. Their magnetic quantum numbers range from -2 to +2. For example, carbon has 2 electrons in the 2p orbitals, and each one is assigned a different magnetic quantum number. The fourth and final quantum number is the spin quantum number, denoted by ms. According to Hund's rule, each orbital can hold a maximum of 2 electrons, but their spins must be opposite, one with a spin positive half and the other with negative half. This is important because even if 2 electrons share the same orbital, they cannot have the same set of quantum numbers due to their opposite spins. This principle ensures that no 2 electrons in an atom have identical sets of quantum numbers. For example, look at the complete set of quantum numbers for the only electron in hydrogen. In helium, each of the 2 electrons has a unique set. Here's the set of quantum numbers for the last filled 2p electron in carbon. Note that the first electron to fill an orbital is generally assigned positive half spin, which is why positive half appears in the set. Also, it's not incorrect to use -1 or +1 as the magnetic quantum number instead of 0, because we don't know the exact orbital where the electron is located within the degenerate p orbitals. However, we typically assign values in the order from -1 to +1. Consider the set of quantum numbers for the last filled electron in oxygen. It has negative half, because that orbital was already occupied by an electron with positive spin.